In this video, we'll work through our second consideration here for explaining the reactivity in nucleophilic acyl substitution reactions. The second consideration is a trend in the structure of the transition state. So structure of the transition state. We're going to approximate the energy of the transition state by considering the structure of the tetrahedral intermediate. So I'm going to scroll up to the content that was in the second video for today, and this was the general reaction scheme here, the general reaction mechanism. And this tetrahedral intermediate here, this structure is what we will use to approximate the overall transition state energy. So as these reactions are occurring, we start with our original acyl group and we end with that substituted acyl group. The reaction has to occur through a mechanism where activation energy is required for steps to occur. And so having different energies of this tetrahedral intermediate, or approximately our transition state, can give us information about why some reactions occur more rapidly than others. So we will be using that general tetrahedral intermediate to approximate that transition state energy. So going back down to our current notes, we're thinking about the structure of the transition state, and more specifically, the polarity of this general Y group and its effect on the stability of the transition state. So let's redraw the general intermediate structure. And that was our acyl, or what was our acyl group. Now it's tetrahedral. So we have a negatively charged oxygen. We have this carbonyl carbon bonded to the Y group, and then the nucleophile has added. So this is a tetrahedral intermediate structure. Now, our Y groups are to some degree electronegative. So they withdraw electron density from the carbonyl carbon. And of course, we have this negative charge on this oxygen. So that negative charge there. Now, the oxygen being electronegative induces a partial positive charge on the carbon. The Y group, if that's also electronegative, can also induce a partial positive charge on that central carbon. And so we represent that with this kind of positive charge. Not positive charge, but this perpendicular line in the dipole arrow. So having this negative charge on the oxygen and partial positive on the carbon, These are opposing charges. Having a negative adjacent to a positive. Now this is a favorable interaction. And so this lowers the energy. If we have a stronger partial positive on carbon, that would lower the energy of the transition state. So if we draw the more specific intermediates, we'll draw them side by side here. So we'll have amides, esters, anhydrides, and acid chlorides. All of these structures look exactly the same as what we have above, just that Y group is changing. So for an amide, that's a nitrogen. For an ester, it's an oxygen. For an anhydride, it's the oxygen plus a carbonyl. And for an acid chloride, that is, forgot the nucleophile here. For the acid chloride, that is a chlorine. So now looking at all of the Y groups, we'll highlight them here. NR2, OR, OCOR, and the Cl. Well, nitrogen is the least electronegative, so that's not pulling as much electron density away from carbon. Oxygen is slightly more electronegative than nitrogen, so that pulls electron density away from carbon a bit stronger. And hydrides, we have another oxygen, but with this carbonyl right here. And so that carbonyl contributes to electron withdrawing. Remember, carbonyls are electron withdrawing groups. And then lastly, we have chlorine, which is even more electronegative, pulls electron density away from that carbonyl carbon. So if we copy down the trend here where amides, less reactive than esters, approximately the same as carboxylic acids, less reactive than anhydrides, less reactive than acid chlorides, increasing reactivity from left to right, from left to right, we also have increasing polar stabilization of the transition state. So the transition state, as you go left to right, is more and more stable. So that means the transition state exists at a lower energy. So less energy is required, less activation energy is required for the reaction to take place.